Perfect. And thanks everyone for attending this talk. I know we're not all in Hawaii together and we're kind of under strange circumstances, but we really appreciate everyone's time and we hope this is a valuable experience for everyone. So our talk is Secrets Are No Fun. So we got rid of them. It's really our story on how we were able to, at Snap, remove a large class of secrets and along the way, just enhance a lot of other parts of our security program and solve a lot of other security problems. So I'm Winston Howes.
And I'm Savanah Frisk. As you guys just got a great introduction, I grew up on Kauai, and I'm really sad that I'm not there right now. We both work on the application security team at Snap. And so we're here to give the rest of this presentation.
Yeah. So when we were looking at secrets, and trying to figure out how we can solve a lot of our problems related to secrets and secret management, we first wanted to understand, why do we even have secrets in the first place? And we realized there's two main categories. The first one is authentication, and secrets are used both for authentication between two internal services as well as internal to external. And the reason I break that out will make more sense as this talk goes on, is we have different solutions for those two different cases. And we noticed that this was actually the largest use case by far in terms of developers having to write code to manage their secrets. And then the other case we have is encryption. And so that could just be encrypting data at rest or signing various payloads. And that was a much, much smaller case. That's actually still an area of active investigation for us and exploration. Right now, the best advice we can give is please use a KMS for managing those secrets. We really want to dive into the authentication case here. And so when we're looking at secrets and kind of why it's a problem, we understand this is an industry problem. I mean, very consistently, we see things about secrets being leaked in source code. We catch this within our own security reviews inside of Snap. And the reason this is such a fundamental problem is when we think of our security programs, we really want to architect our systems in such a way that if all of our source code was leaked, our security would be fine because we've got a few secrets which we've managed to hold on to, and those are separated from source. And our security shouldn't depend on our source code. And so when secrets are mismanaged, it really undermines one of the fundamental premises of our security programs. And kind of coupled with that, when we started digging into secrets and authentication, we noticed that just authentication is tricky. And it's one of the common things we see during security reviews inside of Snap is either misimplemented authentication or missing authentication. You're going to go to the next slide. And part of the reason it is tricky is it's just hard to get right. There's a lot of there's a lot of cases where you can be sort of misimplementing it and not understanding how it fails. OAuth is a perfect example of that, where if you don't follow the protocol to the spec, you can get some very interesting edge cases that come about. But on top of that, there's also a really wide diversity of authentication methods to choose from. So it's not always obvious which one to pick. And they have different strengths in terms of how secure they are. And to make things even worse is even if you were able to standardize on one authentication method within your own company, there's no industry standard. And so as soon as you start integrating with third parties, you have to start adopting these other authentication methods. And that leads to just a lot more complexity. So taking a step back and looking at all of that, we had a few goals in mind. The first and foremost goal was we wanted to reduce secret proliferation. The second one was we wanted to enforce a standard auth mechanism for internal service authentication so that all of our developers, there's only one form of auth that they have to think about. But then kind of extending that and extending this idea of only having to care about one type of authentication, we wanted to reduce the one-off auth implementations that developers have to care about when talking to third-party services. And then finally, we also wanted to get finer grain access control. We realized a lot of times, particularly when talking to third-party services, GitHub's a great example of this, where you get a token and it just has more permissions associated with it than you want. So for instance, at least how it used to be is if you wanted to write a comment in GitHub, you had to give write access to that repository. which was really problematic. And so we wanted to see if we could scope down the access to a much more granular level. So I'll turn it over to Savanah to walk us through our solution.
Thanks so much, Winston. So I'm going to talk next about the overall architecture and approach that we use to meet the goals that Winston just laid out. So the first piece of the puzzle in deciding on an internal authentication mechanism is basically making sure you have a standard way that internal services within your organization can talk to each other. And the reason that this is the first piece is because you want to sort of eliminate an entire class of secrets that need to be shared. And so in our case, if internal service A wants to talk to internal service B, we would like them to stay within the company infrastructure, stay off the internet, and authenticate without having to manage the secrets themselves, without having each developer having to manage the secrets. So at Snap, we leverage cloud-based identity management to do this. For the most part, if two internal services are trying to communicate at Snap, they follow this internally developed protocol. So if internal service A wants to talk to internal service B, they first reach out to a cloud identity provider, which in our case is Google, and they receive what is essentially a JWT token. This token is then attached in a custom header and sent to service B. The token is really short-lived. And again, those secrets are never touched by service A and service B. It's brokered by that identity cloud provider. Service B then validates the token with the provider. And so this internal auth mechanism meets the requirements that we've laid out for internal sort of secretless authentication between services. This was actually developed at Snap before us. And so having this mechanism is going to enable all of the things that I'm going to talk about later. So if you are trying to build a service like we're going to lay out here, you want an internal auth mechanism that meets these requirements. Pushing auth secret management to the infrastructure layer so that developers don't need to manage secrets directly. As I mentioned, we leverage cloud identities for this. It should be uniform across all internal services. There shouldn't be exceptions for different kinds of services. It should prefer short-lived secrets to reduce the risk of replay attacks, and it should heavily prefer an implementation that does not send the actual secret over the wire. So as I mentioned, JWT or MTLS is another example of an infrastructure managed auth mechanism that meets these requirements. So that's all well and good, but what if your internal service needs to talk to an external service? What about external auth? So that's the piece that we really need to solve to get our service up and running. In the past, if your internal service wants to speak to an external service, that external service probably doesn't speak the internal service auth, and it likely is one of the following mechanisms. A shared secret like basic authentication or an API key. Maybe they use OpenID, HMAC, or some other custom auth implementation. This means your internal service needs to implement one or more of these auth types. The traditional approach for this is to use a centralized secret management solution, so KMS, to expose your internal service to the internet so it can receive requests from a third party, and for each service owner or developer to manage the auth implementation and the secret for their service themselves. So the big idea that we're sharing today is, what if we managed all of that for developers? That is the crux of the service we are describing today. So we've implemented something called the auth translation service, which sits in between internal services and external services. The overview of our approach is to abstract the secret management from the internal services, to keep those services off of the internet, and to have the auth and secrets managed by one team. In our case, this is the security team, but other teams like infrastructure teams would be also well positioned to take this on. And so that's really what we're going to dive a little bit deeper in. I'm going to talk more about the auth translation service. The auth translation service is a forward and reverse proxy, which translates authentication. See what we did there? It connects internal services and external services in two ways. We directly proxy traffic. Usually this is from internal services to external services, but it can be used for the other way around, external services to internal services, or from external to external. You can directly proxy between any two services. And then we also have an asynchronous flow, which operates like a pub sub and fans traffic out to a set of subscribed services. This is generally used for external service webhook traffic, but it can also be used, again, the other way around, to fan out from internal services to external services. We've just found that this asynchronous flow is super particularly useful for webhooks. Okay, and so I'm going to go into the sort of architecture of both of these flows. For the direct proxy, the case that we often leverage this for is using external service APIs, but again, it could be used for any two service connections. So when the internal service needs to speak externally, again, we mentioned that internal service authentication protocol that we use. So it starts out by reaching out to the cloud identity provider and getting its identity from there, and then forwarding that short-lived token in a custom header onto us, the auth translation service. And just a note, we abbreviate auth translation service to ATS. So if you hear me say ATS in the future, that's because that's the abbreviation we use for the service. So ATS receives that custom header. We reach back out to the cloud identity provider to validate it. And then our service basically checks or identifies the sender and the type of authentication to use, right? And so in this case, the sender was an internal service and we were using the internal auth. And then it checks authentication by validating, it checks authorization by doing a check against the internal config. And so we use this internal config to let us know what service the internal service is trying to reach out to and what APIs it's allowed to access. And we determine where to proxy traffic to and what external authentication to use by doing a database lookup within our service. We then fetch the secret for that destination external service from a KMS solution and forward the request on. So that's the direct proxy flow with the correct external service authorization added onto it. Next, we're going to talk about the asynchronous traffic flow. And again, this is most commonly used for webhook traffic, so that's what I'm going to talk about. So if an external service has a webhook that's destined for some internal service, it points the traffic at ATS, and ATS then does a lookup for the type of authentication to check. It pulls the secret from the KMS service. And then we do our internal config check to see which internal services are subscribed to this webhook. When we fan out to the internal services, ATS adds the internal service auth, again, by getting the cloud identity for each destination service and adding that custom header, and then fanning out requests. So that's the other major flow. We have one other flow I'm just going to touch on briefly, which is refreshing auth tokens. So if either of the external service flows that I mentioned before require an authentication type that needs to refresh an auth token, we have that ability by periodically reaching out to external services with the refresh token, retrieving the new authorization or access token, and storing that away in the KMS for later use so that it's up to date when needed. Okay, so those are the main architecture flows that we have going on in ATS. Next, I'm going to talk about some of the implications and things that we get from having these flows. So our service becomes a broker for many potential sensitive secrets, access tokens, API keys. And previously to ATS, we had a different token for every use case. So every service had their own token. But now we're able to cluster things together. So basically, we've identified that about 90% of the work that our internal services need external service access for is non-sensitive. And so, for example, posting messages into Slack or sending emails with SendGrid are determined to be sort of non-sensitive. We don't need to re-review those from a security perspective every time. And we're able to have one integration or scoped token for these non-sensitive but high-use operations. And then for the remaining percentage of work, it's a it's a lot less of the work, and they are generally more sensitive use cases, but then we have the ability to work with service owners to add individual credentials for individual use cases, and that was the case before ATS. We also have the ability to automatically add service owners so they can audit changes to these sensitive integrations, and we're keeping service owners in charge of their own ACLs there, giving them the tools to audit and access their own integrations. And additionally, we're providing the added benefit of auto-approving all of these predetermined and luckily high volume non-sensitive cases. So we're able to group credentials in that way. Additionally, we scope the token or the access to the service even further than what the credential allows. Winston touched on this at the beginning, but GitHub is a perfect example of this. In the past, if a service wanted to post a comment to GitHub, we would need to provision them with an API token that also had full write access to the repo, which would potentially allow an external service to write code to snap repos, which is not ideal. So now using the ATS config, we can restrict services by URL path, by what API they're hitting. So in the case for commenting, the API path there is unique from other write actions, so we can restrict integrations to only use that path. And that adds a granularity that the credential itself cannot provide. We're also able to restrict by method and body. Obviously, we're very HTTP focused here, but you could theoretically do different things for other protocols. Our config check is best effort. We don't modify the request. We just validate that it matches what we expect should be allowed for each integration that we support. So that's our finer granularity. And by now, I am sure you're wondering, what do you need to know to build your own version of this proxy? So there's some other top considerations that we have for building a reliable proxy that we want to share. The first is we have two noisy neighbor problems that we ran into, and so we're going to talk about those. The second is choosing the right architecture for rolling back. And the third is how to design for scalability. So let's talk about the first noisy neighbor problem that we have. So let's say a external service has a 1 QPS rate limit. So under the assumption that we have multiple internal services leveraging one connection with an internal service, this means that if any one of our internal services sends 5 QPS through ATS, it'll monopolize the traffic and potentially block the other services from sending traffic during that time frame. To mitigate this, we would impose a rate limit of less than 1 QPS on each of the connections from internal services to ATS. So we would have a little bit less of a rate limit than the rate limit that the external service dictates. And then we alert on integrations that approach the rate limit of the third-party service to begin the work of adding new integrations with that third-party service. Basically, we're able to shard traffic between integrations with the external service, so we have multiple integrations that we can use if necessary. And in some instances, we have high QPS integrations that need their own dedicated connection due to the priority and volume of the traffic. And so we could have a direct connection there if needed. And that helps solve the first noisy neighbor problem. The second issue that we have is when it comes to webhook traffic. An external service webhook might be sending traffic to be fanned out within ATS. To do this, we leverage a queue to store and retry requests. Currently, we use Cloud Tasks. And any queue that you use will probably have some kind of bandwidth cap, which means if a large volume of requests comes in from one service, they can starve the queue resources, which prevents other services from processing. One solution to this would be to shard traffic between different queues, which frees up more resources. However, you still have the issue of one service potentially hogging all the queue resources here if the spike is larger than the amount of queues you can have at the ready. So a full solution to this takes a round-robin approach. You can write requests as they come in to a GCS bucket or some sort of bucket and associate that bucket with the service that they originate from. Then a cron job can pull one request from each bucket and feed it into the queue. This way, large spikes in one service don't cause delays in processing for the other services, and that backup of requests will be stored in GCS, but each service will still get its fair shot at processing. The other issue I mentioned is rolling back. So we use a config file to look up integration authorization, as I mentioned. It's a JSON file that allows developers to add their services to talk to existing integrations within ATS. And one thing we wanted to highlight here is that if the config is deployed within the same code base as the main service, any issue which requires rolling back in the main service also rolls back the config. This causes newer integrations to be rolled back as well. So to avoid this issue, we recommend separating the config and the service code base. One proposed architecture for this would be to write the config to a GCS bucket and then have ATS pull periodically to update the config there. And that allows us to roll back safely while maintaining the most updated list of integrations. Next, I'm going to talk about scaling. So you really need to plan for all the different types of scaling issues for a reliable proxy. Specifically, there are a highly variable number of requests, size of requests, and protocols being used by these external services that we onboard. This has led us to a general strategy of over-provisioning instances and having sane auto-scaling policies, particularly if you're subject to spikes. However, if you have similar traffic profiles for all of the external services that you plan on supporting, over-provisioning might not be necessary. But for us, we found that we have a variable amount of requests that come in. So having a standard authentication mechanism for internal service communication was one of the key components of the proxy that allowed us to achieve some of the bigger organizational goals that we have. This allows developers to focus on implementing that internal authentication mechanism, and they don't really need to focus on anything else. And then we handle the rest. And what this means is that this whole side, the internal side of our application, scales really well, right? Because we only have to worry about one type of authentication and our services only need to worry about one type of authentication. Basically, that scales on its own. On the flip side, the third-party service authentication can be very variable. There's pretty much infinite amounts of third-party service authentication that we could need to support. So we need to be able to scale that well as well. And so we built ATS in this really flexible way where it doesn't necessarily care if something is internal or external. We have the ability to add any type of authentication onto that. We basically just need to know how it processes what it's coming in, how to proxy it, how to add authentication, or what authentication to add, and where to send it to. And so moving on from the idea of like scaling only authentication for external services, we achieved the flexibility that we needed by not defining integrations as code, but rather as a set of parameters. In our case, these parameters are stored in a database, data store. And just, I'm going to talk about something else really quick. One of our parameters is hostname at the top there. An important part of our architecture is knowing where to route each request that comes in. And we do this by essentially using a wildcard cert to receive traffic to any subdomain. So we set specific subdomains for integrations clustered around service. For example, Slack traffic would be sent to a subdomain including Slack. And then we would know by setting this hostname parameter for our integration to look up the rest of the integration details associated with that hostname. So these are the rest of the parameters that we define for an integration, which is API origin, that's where to send the request, receiving auth, what authentication to process on the inbound request, sending auth, what authentication to add on the outbound request. And we have a little S there, sending authentications, because we have the ability to add multiple different types of authentication when we're processing the outbound request. Specifically at Snap, our infrastructure makes it so that if we host an external service on-prem, we bring it on-prem, that means that we then do that internal service authentication that I mentioned at the beginning for that service. But then sometimes the service itself is built with its own type of authentication. So then it would require two types of authentication: the internal service authentication that's required for hosting it on-prem, and then potentially another type of authentication built into the service. So our infrastructure dictates that sometimes we need multiple types of auth processing. So we add multiple auths in some cases on the outbound request. And so the last item for our sort of abstract integration definition is a rate limit. And this, again, allows us to define rate limits per integration. So this parameter-based approach allows us to configure integrations easily and also scale easily, because we can ad hoc add new integrations under this pattern. So additionally, rather than updating our code base every time we add an integration, we have an API that allows us to determine the types of authentication that we use and the parameters of that integration in the database. So when we are ready to add a new service, we update the database. And in the event that we need to update a new type of authentication, these scale by having general auth plugins of a sort. And so when we write one authentication mechanism, we don't need to rewrite it or write it specifically again for a new service. Unless it's super custom, we can reuse these auth plugins that we've built in the past, like shared secret, basic authentication, HMAC plugins, any plugin that you could need to pair with new integrations. And so that's how we keep things generalized and keep things scaling. And as you can see, our proxy can pull from the database of integrations and pull from the different auth plugins that we have available, which allows us to add a large number of things fairly quickly. So the next thing I'm going to talk about related to scaling is the operation work that we have. This service comes with a lot of ops, including managing integrations with third-party services. So we receive a lot of questions on how to integrate with these third-party APIs, since we are the people that generally helped people get set up. I'm now an expert on the Slack API. Our service is where people come first if the third-party service has an outage, and we often identify outages first since we sit in the middle there. And we're also responsible for adding new authentication mechanisms if we get a service request for something that we don't have a plugin that's already written for. So how we manage this operation work is to cluster integrations by service, like Slack or GHG integrations. And as much as possible, we empower the service owners, so that could be IT or DevOps or infra teams, to own the integration with ATS in terms of making changes, approving additional internal services. We have owners files that have clear directives for adding new services and people to ping, and then having good ownership of those external services and knowing who those owners are and having good relationships with those teams. All of that makes it possible for us to sort of get out of the ops crossfire, but more importantly, to put someone in the path that can effectively handle the situation and knows the correct answer to the situation because they are that service owner. To make this possible, we report on a lot of metrics, latency being one of them. We want to make sure if we're adding latency to anyone's service or if it's impacting their performance at all. But more importantly, the errors that we report on, we draw a big distinction between ATS-generated errors and third-party service errors. So if our service errors, we want to know that it was caused by our service, and so we can have someone who's going to give attention to that immediately, versus if the third-party service is erring, we want to surface that back to the developer so that they can contact the third-party owners directly and triage that issue with them. So that's not something we would want to get in the middle of. We want to empower developers to reach out directly to third-party services in the event that they have an error. And with all of that said, I'm passing it back to Winston for some of the additional considerations we had when building out the auth translation service. Thank you.
Thanks, Savannah. Yeah. So in addition to a lot of the stuff Savannah talked about, like servicing metrics to developers and just a lot of the other scaling things, there's some other considerations to have in mind if you're building a proxy like this. So the first one, there we go. First one is that so while we were able to standardize auth inside of Snapchat, and we were able to give developers just one authentication method to use, whether they're communicating internally or externally, we still have these weak forms of authentication just pushed upstream between ATS and these third-party services. And so we're not really able to get away from that. And it does have a negative effect in that some of these forms of authentication actually have secrets in the URL, which means they're going to end up in ATS logs. So something to just keep in mind, and something we've been doing is we've locked down the logs to just the project owners, whereas like logs generally across Snapchat shouldn't have any secrets in them. Our logs are particularly more sensitive. And so because of that, we have guidelines for when people interact with the logs and need the logs. And they're not exported as widely. So that way we're able to just control secrets that end up there. Next consideration is ATS is an incredibly appealing target for attackers. That's something we want to like openly acknowledge, that if this gets hacked, that does suddenly give hackers a lot of access to really all of our integrations with third parties. Additionally, if ATS goes down, we're going to just have really widespread outages across Snap. The flip side of being a single point of failure, though, is it's also a single point of focus. And so it allows us to just really make sure this service is hardened. And specifically because it's managed by the security team, we're able to build the service with security best practices from the ground up, as well as reliability practices by partnering with some of the other teams and just getting their expertise in this. The other thing, which is I think really, really critical that ATS provides Snap, is because it's providing just a single layer of authentication or a single mechanism of authentication across Snap, it provides us a standard which reduces complexity dramatically. And as we know, complexity is the devil of security. And understanding a vulnerability is just a developer making an assumption but not validating that assumption in code. Reducing that complexity, reducing those assumptions that they have to understand, has reduced a large class of vulnerabilities across Snap for us. The other two cool benefits here is we now have a centralized way to audit all our connections between third parties. And that's incredibly helpful during investigations and just being able to inventory what's happening, especially at our scale where it's hard to keep track of things. And then finally, we've deduplicated a lot of work. People don't need to think about implementing authentication over and over again. People don't need to think about how do we store keys and handle all of that. Security team's done it once for everyone across Snap. So yeah, we've saved a lot of engineering hours with this. And then finally, last consideration is we do have these teams whose mandate is to manage the relationships with these third parties. And so when we're taking some of that power from them, but they're keeping that mandate, that's something we want to be very careful and mindful of. And so the teams in particular that we identified across Snap as being good partners here are IT and our tools, our DevOps team, and then some of the product teams also own integrations with third parties. And so we wanted to create incentives for everyone. So this is a win-win. So one of the incentives is these teams have significantly reduced time having to issue keys or anything because we're able to reuse keys for a lot of these non-sensitive use cases. We've saved many, many hours on all of these teams' side of having to reissue keys for every single use case. Additionally, there's also just less engineering resources needed to integrate with these services. You don't need to look up the auth. You don't need to figure out how to manage keys. On top of that, because everything's in these centralized configs, you can see how other teams have integrated with third-party services and pretty much copy-paste what they have. This is one of those times we've used copy-paste as a benefit here. And so teams are able to get up and running quicker and integrate much faster with third-party services than they were prior. Next slide. Cool. So with all of that, I just want to kind of close things out with some of the lessons we learned along the way. The first lesson is when we looked at this problem, rather than trying to educate developers on storing secrets in a KMS, things like that, we wanted to understand fundamentally, why do developers even need to care about this? And abstracting away the reason for these security failures was really helpful in that it gave us insight into providing a much more holistic solution, which is a lot more bulletproof than just hoping for people to do the right thing. The next lesson we had was around just making our services generalizable, particularly defining integrations in this programmatic way and allowing us to onboard third parties programmatically rather than having to write code every single time has allowed us to scale dramatically, which is really helpful just in terms of getting the entire company onboarded onto this thing and being able to accommodate all the various needs. And so keeping things highly generalizable has been just a real win for us. We didn't start that way, and we kind of shifted to this approach, and it's just allowed us to scale. And then finally, offering other engineering teams a carrot. Again, these partner teams in particular, really are trusting us to maintain these integrations and keep things up to date and working. And so in order to do that, we needed to just build strong partnerships. And one of the key ways to do that was by offering them lots of benefits. And so in this case, it was saving them a lot of time on issuing keys, on even answering questions, because it's much clearer for developers. They can see how everyone else is integrated with these third parties, and they can just follow suit much more easily. So thank you all so much for your time. We're able to sleep better at night now. And we've got a few minutes left, so we wanted to take any questions if people have them.
All right. What a fantastic talk. Thank you all so much. Thank you both very much. So let's get right to questions. Question one, how are you propagating identity to downstream services, like end-to-end, using this model, like user to UI, to app one, to app two, etc.? Is that a good question?
Sure. Yeah. So when we look at our services, all of our services have an identity which is managed by the cloud. So we're leveraging cloud identities there. In terms of actual identity of like service talks to ATS and kind of propagating that all the way through to the third party service, the way that we're doing that is we're using host names as sort of the routing structure within ATS, so that way we know exactly how to route them. And then we're using that config where they've entered in some of the information about like the identity of their service. And so that way, when they make a call to us, we can look at the config and say, this is the identity we're expecting, validate that the identity they've given us matches up with that cloud identity, and then propagate that request on. Does that answer the question there, or is there more to it?
Anything to add, Savanah?
No, I think that's it. There's two different identities: the internal service identity based on the cloud identity provider, and then the host name that we use to sort of identify the integrations.
Next question is,
configs tie this together. Yep.
What are your thoughts on Istio for service AAA authentication, authorization, and audit? So, any general thoughts on Istio?
It's maybe actually Winston, something I don't have any thoughts yet.
Yeah, sure. It's something we looked at, and we actually are looking at as a larger, just sort of authorization approach. I think we ended up going with something a little more custom, though definitely, we like Istio. I think it's a good model. A lot of our inspiration for it's a broader subject than just this talk, but our general authorization structure or framework that we're kind of imposing on all of our services is very heavily influenced by Istio.
Someone's asking, do you consider JOT a secret? Do you have any proof of possession implemented with JOTs? Is there any reason to prefer JOT over mutual TLS for service auth? That's a lot to unpack there. Yeah. Is that an acceptable question?
Yeah, we can try to take them. I do consider they can be used as secrets. I mean, in terms of preference over MTLS versus JOT, I actually think for us, I don't know of any actual preference. We actually had a debate internally about which one to go with, and I think it came down to a performance issue. And we ended up using, well, in our case, we used JWTs all over the place. Yeah,
And
that's my very quick.
Just to add to that, that's the reason we mentioned both of them, because really the requirement for a service like this would be to push the secrets out to an infrastructure layer rather than having the services manage them themselves. And so both of those satisfy that.
How do you handle SDKs where the use is a client that needs a credential?
Yes, great question. So in a lot of those cases, we ask just people to put in like a dummy value, like a secret, and then we just ignore it on our end. The real key to an SDK is we need to be able to change the host name, and a lot of SDKs allow you to do that. I'm struggling to think of any SDK we've encountered that hasn't allowed us to overwrite the host name. Well, sorry, I take that back. You need to do two things. You need to overwrite the host name and add a header. Thankfully, because of how our infrastructure is set up, that header is actually just added automatically when any developer makes an outbound request to another Snap service. So they don't have to worry about that at an SDK level. So in our case, it's overriding the host name. But the fundamental two things is you need to add a header in order to authenticate internally, potentially, and then you need to add the host name.
Savanah, Frisk, and Winston House, what a fantastic talk. I'm grateful you spent that time with us. Thank you again very much for your time. Great talk.
Thank you all.
Thank you so much.
Really appreciate it.